Is Anindya Datta. At present, I'm head of the Department of Chemistry. It's a pleasure indeed to introduce our colleague, Professor Maheswaran Shanmugam, who has received this prestigious IRCC award for his publication. Well, Ishwar, as we call him, had joined the department in 2011, I think. Before that, his MSc is, up till MSc, all his education is from Tiruchirappalli. Bharatadasan University is where he got his MSc from. Then he joined University of Manchester for his PhD, following which looks like he took a liking to California. So he did his postdoc in as many as 3 universities of California, in Davis, San Francisco, and Berkeley, before joining here. So Ishwar works in the field of molecular magnets, interest in which transcends barriers of chemistry or chemical sciences, because these molecular magnets have a lot of application in things like qubits, in things like storage of information, and so on and so forth. But for a chemist, other than these applications, what Ishwar has shown is that you can also use them to activate small molecules like oxygen and so on and so forth. It's a very, very dynamic research group, a dynamic and enthusiastic researcher himself, published a lot of good papers, done a lot of significant work, and that is why he has been recognized with this award. Over to you, Ishwar.
Thank you, Dr. Anindya, for your kind introduction. And so good morning to all. I really take this opportunity to thank IRCC for providing me this award, recognizing our research effort. And the theme actually we have submitted to IRCC was, so can we use diamagnetic metal ions to improve the magnetic relaxation of paramagnetic lanthanide systems? Particularly what I'm going to talk about today, it's the dysprosium ion in this particular case. Okay, so I just wanted to highlight, I'm not going to go into the details of it much. I just wanted to highlight, so what is the importance of a diamagnetic metal in improving the magnetic properties of lanthanide systems. Okay, as we know already, so the diamagnetic metal ions has its own applications. See, for example, the superconductors, one of the best diamagnetic example, so which can be used to generate a strong magnetic field. Say, for example, in spectrophotometer up to 7 to 14 Tesla, and we can also generate 45 Tesla of a magnetic field. So, which is been developed in National High Magnetic Field Laboratory in Florida. In fact, the same laboratory, or Los Alamos laboratory, has managed to make a 100 Tesla pulse magnet field using a diamagnetic material. And similarly, so one of the important properties of a diamagnetic material is that these magnetic materials will be repelled by the external magnetic field. As a result, one can have magnetic levitations. In fact, we can levitate any diamagnetic materials in under this condition. Even a human being is in a diamagnetic material. We have to have a very strong magnetic field to levitate in this particular case. So this video actually shows that is the diamagnetic material is being levitated under the strong magnetic fields. Like in this case, we have a strong electromagnet, and using this basic principle, one can actually develop a commercial application of maglev trains, which is one of the fastest train in the world. One can have it. So the train principle is based on this diamagnetic material. I mean, this diamagnetic material repelled by the external magnetic field of these systems. So another important application of this magnetic material is commonly used for a magnetic dilution. So essentially, when you have an intermolecular interactions, one molecule to another, in order to prevent such kind of magnetic interactions, so we dilute this one using a diamagnetic material. But how to use this particular magnetic diamagnetic material for improving the magnetic properties of a paramagnetic ions not been studied in details. So this is where that we have taken up this particular challenge, and then so try to see how one can able to use this properties. Okay, And so before we go into that, since I'm going to talk about a lanthanide based system, I just wanted to introduce some of the basics. Okay, so in lanthanides it has seven f orbitals are there. So don't worry about the labeling of the orbital which are so given. I just wanted to draw your kind attention that this ml values, so there are ml values of plus or minus 3, ml values of a plus or minus 2, ml values of a plus or minus 1, and 0 is there. So these are the classification under which. So if you notice that the orbitals with the largest ml values are mostly oblate in nature. That means their electron density or the orbital shape is like in the xy plane. As the ml value decreases, the extent of oblatity it is actually decreases and eventually becomes an prolate ion. So why I am introducing this, that eventually you will understand in a couple of slides later. And one another property is that so what I'm showing on the right hand side plot, I'm not going to go into the details of it. The take home message is that in this particular systems, the 4 of orbitals are actually buried inside, because the other valence orbital like a 5s 5d and then 6s it is shielding. As a result, the 4 of orbital does not interact with the ligand orbital very strongly. So what will be the consequence of this? So the 7 orbital which I shown here in the previous slide, which will not the degeneracy will not be so lifted, it maintains its degeneracy. As we know, so if I'm having only one electron in the, say for example in this particular orbital, so the electron spins by itself. As a result, it creates a spin only magnetic moment, and this electron is revolving around the orbital. As a result, it creates an orbital angular momentum as well. But the spin and the orbital angular momentum couples together. As a result, what we have, it is in a total orbital angular momentum. So this total orbital moment, the number of state it is generated by the coupling between the spin and the orbital is given in this equation. So without going into much details, I can clearly show that. So this is a free electron, the term symbol that what we are trying to give here. And because this spin and the orbital coupling of your system, orbital moment coupling, so we get a state of j state, what we call it as a total angular orbital momentum. So it is 15 by 2, 13 by 2, and so on. So if you look it up here, the energy gap between these two states, it's extremely high. So hence we can able to explain the magnetic properties of these systems only considering the ground multiplet level of this particular system. So since I'm talking about the J level of a 15 by 2, there are 16 states are possible. It exists in the 8 pairs. So this 8 pairs can be lifted in degeneracy by considering the perturbation called a crystal field. That means now I'm going to place a ligand field around the metal ion. As a result, that it splits these 8 pairs of system. So this can be represented in this double well potential. So that's what I'm showing here. But the important point is that the energy gap between the energy barrier between the 15 over 2 to the over plus or minus half it is here. What determines this energy gap? So this is the first question that I wanted to address here. And it actually translated in terms of like what is the actual energy gap between a 15 over 2 to 13 over 2, 13 over 2 to 11 over 2, and so on. So the second point is that if I'm representing this 15 over 2 as an upspin orientation, and suppose if the spin wants to change its orientation to a downspin, whether it is going to climb over the mj ladders completely, or it will be just goes to the first excited Kramer or second excited Kramer, and then it just tunnel through it. So this is absolutely controlled by a crystal field. Even though the crystal field is very weak, the importance of a crystal field is particularly important for determining the magnetic properties of your system. So what I'm showing here again, it's the orbitals which we have shown in the previous slide. Suppose if I'm taking a gadolinium, it is an F7 electronic configuration, which has one electron in each orbital. So if you look it up under this condition, so the f electron charge cloud will be spherical in nature. As soon as I introduce an eighth electron, so this will be occupying the plus or minus 3 ml levels here. As a result, so now you can look it up, the f electron charge cloud becomes an oblate shape. That means the f electron density is in an xy plane. So in order to stabilize on a largest mj value, which is one of the important aspects to have to store the information on the molecule, So you need to have only the ligands along the above and below this particular plane. So this is what that I have shown, one of the best example known in the literature so far. So this is a dysprosium ion. Above and below there is a dicyclopentadienyl ligands are there. That there are no ligands are around the system. As a result, the spin actually climb all the way up to the plus or minus half, and then it is changes. So you can see here the energy gap now it is becoming from the 15 over 2 to plus or minus half. It is 2000 Kelvin. Whereas it's another best example is reported by Murugavel and co-workers. So if you see in this one, in this molecule also you have the ligands only above and below, and in addition to that, that you have a ligand in the equatorial plane also. So why we have to have, so why it is stabilizing 15 over 2? So whenever you have a ligand only at the above and below plane, so the repulsion between the electron in the ligand system and the f electron system is very minimal. As a result, it is stabilizing in a 15 over 2. If you have a more number of ligands in the equatorial plane where the repulsion is going to be much more higher with the f electron density, so the overall energy gap that what we see here, it is up to 2000, but here it is only 700. And also the spin tends to change its ground state by through the second Kramer state of this particular system. So this is where the ligand field is playing a major role. So we wanted to have an ligand only above and below the system. Now the challenging stuff is that, so the lanthanides are bigger in size. It prefers to have always a 7 to 20 coordination number. So this is the ligand that we made, or this is the metal complex that we made in this particular case. It's the three nitrates around the dysprosium ion. Then there are two ship-based ligand. So I want you to draw your kind attention that this ligand is neutral, even though this is a partially involved in a keto-imine tautomerism kind of thing. So it is a neutral molecule, but it's in a partially charged system because of this tautomerism in this particular case. So what I have shown here, so in this particular case, the nitrate ion is there in that XY plane of the F electron density. As a result, one can expect the barrier for the reorientation in this particular case, it is 22.6 Kelvin. But what I wanted to have it, I wanted to get rid of these nitrates because these are all charged ligands which are present in the XY plane of your system. It's actually deteriorate the property of magnetic properties of this particular system. So how do I remove this one? That is the first question. And then how do I increase the charge density along the XY above and below the XY plane of your system? This is where the diamagnetic metal ion is coming into picture. So when I'm
Just
placing
2 minutes, Shanukam.
yes, yes. So when I'm placing an ligand, when I'm placing a diamagnetic metal ion in the vicinity of this one, so it deprotonates your ligand system. As a result, there is a highly charged density is present at this particular system. And also you can notice that there are now less number of nitrates now. Earlier it is 3 and this is 2 ligands are there. So this molecule is expected to have a better magnetic property or magnetization relaxation dynamics as expected. So you can see now the barrier for the magnetization relaxation is 5 to 6 fold is increased compared to. So the only difference is that I just placed on a diamagnetic metal ion in the vicinity of your lanthanide systems. So how this is happening, essentially we just see the charge density of the ligand. So this is the dysprosium with the neutral molecule, neutral ligand, so where the charge density is around 0.5, and here if you see here it is in a 0.735. So what is the consequence of this additional charge density is that I just wanted to draw your attention. So this is your ground state MJ level and this is the first excited MJ levels. So the energy gap is like around 25, whereas this is close to 90. So there is a threefold or a fourfold increase in the energy gap just by introducing the diamagnetic metal ion in this particular case. So zinc is actually doing good. So is it possible to increase the axiality of the system even more higher? So what we have kept here, like only one zinc ion in between this one. In this particular case, I have a 2 metal ions. So now you can see here there is a highly charged density above and below the plane, and the less number of nitrates also there. You can see here now the computed energy barrier is close to 150 wave number. So this is consistent with what is our proposal. We can use a diamagnetic metals to push the excited state from the ground state of your system, and the magnetic properties can be increased nicely. So what I'm trying to show, this paper was highlighted in Chemcom. So what I'm showing on the left hand side is a small wrestler. So the small wrestler actually doesn't have any proper proper shape. In other words, like I'm trying to correlate, the electron density will be placed over everywhere. When you have such kind of a system, what this will do, the first excited state will be very closer to the ground state. That means the energy gap will be very less, but as a result, the magnetic properties will be poor. But if you try to place a zinc ion in the vicinity of a lanthanide system, it pushes the excited state significantly away and improve the magnetic properties. And this is what that we have followed an unconventional approach developed for the first time and improve the magnetization relaxation of this dysprosium ion. And so of course I would like to thank for my collaborators for such kind of a work. I mean, particularly Rajaraman for this one, and the funding agencies. And all these works is not possible without the help of the students. And this is my current research group, and most of them are left. And this particular zinc work is done by Sapurva. She is currently postdoc in Wayne State University in US. Finally, I would like to thank your kind attention. Thank you.
Thank you, Professor Shanmugam. I have no questions been asked here in chat, but anybody would like to ask one question? Niobium, Professor Nambudri is asking the question. Niobium is also used in superconducting magnets. Which one is better, dysprosium or niobium?
So depends on the ligand field system. I mean, niobium has been used as an superconductor. I mean, it is a perfect diamagnetic material, and yeah. So one can fine tune the magnetic properties of your dysprosium as well as the niobium in this one. So the molecular examples are not there, but the niobium is used as an alloy in this particular case as a permanent magnet. So when it is, we cannot compare at this point of time alloys and the molecular system. So we are trying to develop on a molecular based system, because the storage density can be improved significantly compared to the alloys or the magnetic nanoparticles of the system.
Thank you very much, Professor Shanmugam. Thank you very much. Excellent lecture and in time now. Thanks.